Good evening and welcome. As we begin, I would like to acknowledge the traditional owners of the unceded lands on which we are gathering today, the Wurundjeri Wurrung peoples. We recognise the unique place held by Aboriginal and Torres Strait Islander peoples as the original owners and custodians of the lands and waterways across the Australian continent, with histories of continuous connection dating back more than 60,000 years. We also acknowledge their enduring cultural practices of caring for country. We pay respect to elders past, present and future, and acknowledge the importance of Indigenous knowledge in the Academy. I'm Catherine Bowen, Professor of Climate, Environment and Global Health in the Melbourne School of Population and Global Health, Faculty of Medicine, Dentistry and Health Sciences, and Deputy Director of Melbourne Climate Futures here at the University of Melbourne. And it's my absolute pleasure to welcome you all tonight to hear from one of the University of Melbourne's 2024 Miegunyah Distinguished Visiting Fellows. The Miegunyah Distinguished Fellowship Program is a prestigious initiative supported by the foresight and generosity of Sir Russell and Lady Mab Grimwade. The program enables overseas scholars of international distinction to make an extended visit to contribute to the university's academic, intellectual and cultural life. Sir Russell Grimwade was an eminent scholar and supporter of the University of Melbourne, including as a member of the University Council for 20 years and a period as Deputy Chancellor. The Grimwade family have had an enduring impact at the University of Melbourne, fostering academic excellence, critical inquiry, and the deep commitment to education and knowledge exchange, which has brought us all here tonight. And it gives me great pleasure to acknowledge a very special guest, Sir Angus Grimwade, who joins us today. Thank you to Sir Angus and the Grimwade family for your generosity and support. Professor Ebi has been jointly hosted by the Faculty of Medicine, Dentistry and Health Sciences and the Faculty of Science. So I thank my colleague, Professor John Barnett, for his support for this fellowship and also, importantly, his own leadership on climate change, particularly in the Pacific region, as now the Director of the Oceania Institute. I am delighted to introduce Professor Kristie Ebi, who has joined us at the university for the 2024 Miegunyah Distinguished Visiting Fellowship. So Professor Ebi is an internationally renowned epidemiologist who studies and develops interventions to help at-risk populations deal with climate change. She is Professor of Global Health and Environmental and Occupational Health Sciences with the Department of Global Health at the University of Washington and has been conducting research and practice on the health risks of climate variability and change for over 30 years. Chris, I think we can call you Chris, is eminently placed to positively contribute to the university and to its broader goals to advance the state and national interest and to benefit society. As populations around the world face wildfires, floods and cyclones, there has never been a more pressing time to educate policymakers and the wider community on the health risks associated with a changing climate. Miegunyah, a word of Aboriginal origin meaning house, was the Grimwade's family home. While extreme heat is just one example of how climate change is affecting our health, well-being, and the beautiful planet we all call home, heat offers a critical lens to examine the impacts of climate change, the effectiveness of our current responses, and pathways to manage the risks ahead. Australia is facing one of the hottest summers on record, according to the Bureau of Meteorology, or the BOM's, weather modelling, which is projecting well above average temperatures across the country. Their forecast, which was released earlier this month, shows a greater than 80% chance of minimum temperatures in the top 20% of years, which the BOM label unusually high temperatures. As we know, though, it's not just in summer when we are feeling the heat, but this is also pushing into spring and winter. Australia recorded its hottest ever winter temperature this year with Yampi Sound in the Kimberley region of Western Australia, reaching 41.6 degrees in August. With Australia facing a summer of potentially deadly heat, how might we better prepare for and effectively manage and govern the health risks of increasingly intense, frequent and sustained extreme heat events? Please join me in welcoming Professor Ebi to help us grapple with this critical question.
I want to thank Professor Barnett, Professor Bowen very much for putting my name forward for this prestigious fellowship, and I really appreciate the opportunity to talk with all of you today. So thank you very much for coming. As Catherine said, I'll be talking on heat, but in the Q&A, happy to talk about other issues related to the health risks of a changing climate. I want to go back to July, not that far ago. The Secretary General of the UN declared heat an emergency for the planet. Heat because of climate change. There's now efforts across multiple UN agencies to ensure that there are more efforts to prepare societies, to prepare our infrastructure, to prepare our institutions to manage the changes that are coming with these increases in extreme heat. We know from the Intergovernmental Panel on Climate Change that extreme heat is increasing in frequency, intensity, and duration. That's already occurred. And going forward, the risks are going to continue to climb as humans continue to burn greenhouse gases and as we continue to have insufficient investment in trying to protect those who are most vulnerable. There's so much information on heat. It's a big topic to cover, hard to select a few points to cover. The first is exposures are increasing and have been increasing over time. You can just look at the patterns. These are data from 1980, showing for older adults, for children under the age of 1, a huge increase in the number of heat days. And that is continuing and will continue as we go forward. Look at my own slides. I put in some data from June to August of this year. This was the hottest season ever. Our records go back quite far. They go back into the 1800s, and this was the hottest. 1 in 4 people have had no break, really, from these rising temperatures. The global exposure peaked in August when 4.1 billion people were experiencing high temperature records. These records were made at least 3 times more likely by climate change. The average person now is experiencing 17 more days per year of risky heat because of climate change. And I'll show you what that means for our health and our well-being. These numbers are dramatic. If you go back just a few years into earlier assessments from the Intergovernmental Panel on Climate Change, there wasn't this emphasis because the temperatures have been changing so quickly and becoming so much more extreme. I didn't put in, there is an iconic figure from the working group in the IPCC that focuses on climate science, and it was showing return periods of extreme heat events. And the most extreme heat event they highlighted was a 1 in 50-year event. We're seeing 1 in 200-year, 1,000-year. And there was an event a few years ago in Scandinavia that was a 1 in 3 million-year event, which I personally find pretty hard to conceptualize. There's a group in the United States called Climate Central who put together a new metric you might be interested in. It's called the Climate Shift Index. And for many places, most places around the world, doesn't get to super fine scales. For every day, it tells you, is this day within the range of what's normal over the long-term average? And this is for a few days ago. These are all the places in the world in red where temperatures were outside the long-term average. I also put in this one because you might be interested in this if you don't know. At Columbia University is an institute called IRI, and it every month puts together a 3-month forecast of what's likely to happen with temperature and precipitation. And this is the 3-month forecast as of a couple of days ago for all countries in the world. Personally, I use this when I want to take a vacation because I look ahead to see what it might be like. I pulled this up and went, I don't think I want to go to Brazil. It looks like it's going to be extremely hot, and parts of South Africa are going to be pretty hot. But you can see the pattern I'm showing, that no matter how you look from different approaches, the answer is always our temperatures are getting much hotter. And it's not just the average, it's the extremes. When you look at what happens in terms of trends with a changing climate, people often focus on the average, and the average is shifting. Temperatures at any location form a kind of a bell-shaped curve. And so what's happening is the average is just moving to higher temperatures. But it's also that the curves are smooshing down and moving further to the right. So there's an incredible increase in extreme temperature. And we care about that because of our health and our well-being. I will not talk about ecosystems, critically important for ecosystems as well. This is a summary figure put together by Ollie Jay, who's at the University of Sydney, physiologist, and points out the ways that heat affect our body. From the human health perspective, what we care is our core body temperature, not what you measure with a thermometer. It's in our, if anybody does Pilates or yoga, it's your core body temperature. Our core body temperature rises and falls during the day. You may go out and take a walk in the sunshine. You may take a run. You might ride a bike. You might work outside. There's a whole range of reasons that you could be in an environment where it's hotter. And your core body temperature will rise as a result. It also rises as a result of exercise, of any kind of work you do that increases your internal temperature. But that core body temperature needs to stay within a pretty narrow range to protect our cells and our organs. We have behavioral mechanisms and physiological mechanisms to keep that core body temperature where it needs to be. When it's hot outside, people go and find trees, they find water, they find someplace where they can cool down. Physiologically, we have a range of mechanisms up to and including sweating, which is important for keeping that core body temperature down. But when the environmental conditions are too extreme, our core body temperature continues to rise. We know from a wealth of studies that after a heat wave, about half of all the excess deaths in a heat wave are from cardiovascular causes. Basically, our heart doesn't want to be hotter. And so people who have underlying heart disease, which is a good fraction of the population, then can be affected by this higher core body temperature. Also affected are people with kidney disease, people with respiratory diseases. You see an increase in lots of different health outcomes following a heat wave, and it all comes back to maintaining our core body temperature. I've emphasized this because then as we talk about what we can do has to help our core body temperature stay within that range. I've put some statistics on the right-hand side, talked about some of the groups that are more vulnerable. One thing that's become clear over the last couple of years is pregnant women are at higher risk during heat waves. That pregnant women exposed to higher temperatures during pregnancy more often have a low birth weight baby. There's undoubtedly going to be more vulnerable groups discovered as more research is done. But we know that overall, it's older adults, it's young children, it's people who work outdoors, people who take certain prescription drugs, people who have diabetes, heart disease. You can hear it's a long list of people who are particularly vulnerable in the heat. And so there's much that has to be done to ensure that those people are protected during these high temperatures. I'll talk a little later about physiological limits. I'm rubbing this thing against something, aren't I? Pacific heat dome was a couple of years ago. I live in Seattle. It affected the states of Oregon, Washington, and British Columbia in Canada. Apologies that the temperatures are in degrees Fahrenheit. The US still uses that. But if you follow your broadcast meteorologist, you know that temperature records are traditionally broken by tenths of degrees. Our temperature records were broken by 5 degrees Celsius. That had never happened before. The temperatures at night would have been records if they'd been daytime temperatures. And that's important because we typically, as we go about our day and our core body temperature rises, our body uses the nighttime period for our core body temperature to fall. And so the temperatures didn't fall at night. We were not prepared as a region. I'll talk specifically about Seattle. We did not have a heat wave early warning and response system. The city and the county did an enormous amount of work to try and protect people as much as possible. They did set up cooling shelters, but that information was not widely available. And it's a real issue with trying to set these systems up at the very last moment. It's extremely hot. It's dangerous. It's during COVID. We have cooling shelters, but what do you tell people who are at higher risk? What do you tell older adults? That they walk to a bus station and wait at the bus station to take a bus to the cooling shelter? Those pieces hadn't been worked out because they frankly didn't have time. There's lots of operational issues with heat wave early warning systems. And the area did as much as they could on very short notice. But in the end, when finally the death certificates came in and the analyses were done, there was more than 440 people in the state of Washington who died during this event. This is 440 people who died just over a couple of days. And these are excess deaths. There was a rapid analysis of this event early on that showed that this event was virtually impossible without climate change. These people died from climate change. And that is a different kind of statement than we've been able to make in the health sector for the last 30 years. Instead of saying that there's associations, we can now say that people are suffering and dying because of climate change. I'll also make some points at the end that heat has an all of society impact. And so thinking about how to address this means you have to include all of society. One of the things that happened in Oregon, and it also happened in London in the big heat wave they had a year and a bit ago, was that the temperatures were so high the railways couldn't run. Rails are tempered to a particular degree. It was too hot for the rails. And so the assumption that people could go to cooling shelters, that wasn't me. Was it? Okay, great. But just to make the point, when we think about the impacts of these events, they're much larger. Another point I wanted to make is there is an area off the coast of Seattle, from south of Seattle up into Vancouver. It's called the Salish Sea. And there's lots of First Nations people, sovereign nations along the coastline. During low tide, the temperatures were so high that more than 1 million clams and mussels were cooked, literally cooked by the high temperatures. And that's food security for these people. Economic security, because that's one of our industries in the state of Washington. And so I'm focusing primarily here on mortality, but that's only a small fraction of the consequences of high temperatures. There's a field within climate change called detection and attribution. It does exactly what the name implies. It detects whether there's a change in a trend and then determines the extent to which that trend could have been altered by climate change. There's quite a bit of work starting now in the health sector, which is a good thing, to do these kinds of analyses. This is a modeling study that looked across 43 countries, over 700 locations. and had data for more than 2 decades in most of these locations on heat-related mortality. And so could look at these trends over 20 years and then paired that with some work coming from the climate science community on detection and attribution. The bottom line is this analysis showed over 35% of all heat-related mortality in the last couple of decades is because of climate change. As you look around the circle, you can see there's a lot to do. There's countries, only one country in all of Africa. There's lots of countries that are missing. You can see there's opportunities to understand why some countries are more or less vulnerable. It's a great first step to start doing some comparisons so we can learn lessons and figure out how to better protect those who are most vulnerable. An area of very high interest, particularly to economists, is looking at worker productivity. Worker productivity is being affected by high temperatures. We all know personally when it gets pretty hot outside, we're not necessarily enthusiastic about working. For outdoor workers, it's even a bigger issue. This is analysis over hundreds of thousands of, over millions of workers, 30 countries, and just starts to show that as workers are working under heat strain, that productivity goes down. And there's lots that can be done. During the Pacific Heat Dome, I live in Washington. We're one of five states in the United States that has rules to protect outdoor workers. And I remember watching the media coverage. It was during the height of our cherry picking season. We lost most of the cherry crop because it was so hot. But I was watching for one of the orchards, every single one of their workers spent time in the walk-in refrigerator. And that was intentional to make sure that they can get that core body temperature back down. So people are creative when you have these rules. They find ways to make sure that they can protect people during periods of high temperature. I wanted to spend a minute on something that's technical, but it makes it into the media quite often. There's a number of studies from climatologists that have looked at the question of survivability, and you'll see newspaper headlines of how we're all going to die in the future. It's obviously relatively sarcastic, but the newspaper headlines often go pretty extreme in that direction. But those analyses were done without actually understanding human physiology. And so this is a paper that looked at survivability versus livability. And it's the first time that clear definitions were provided based on human physiology. And so there is a set of conditions that are not survivable for some people, where it's too hot and too humid. But there's a lot of wide range of temperatures where we can live. You can think across the planet of all the places people live that you think, how could people actually live there? Humans are more or less creative. We've got infrastructure. People live in Antarctica, right? They've built this infrastructure to allow us to live in a variety of environments. And so this is important when you hear about these studies because they haven't made this differentiation. Right clicker. And so these are some of the curves that come out. The yellow color is where people can survive. The row across the top is indoor. Across the bottom is outdoor. The left-hand column are adults, 18 to 40. The right-hand column then are older adults. You can see the black curve and how they differ across these 4 set of conditions. So it's not one cut point where it's survivable or not survivable. The question is, what's the cut point under different kinds of conditions? And when it's really hot and really humid, the temperature we can survive comes down. When it's less hot, less humid, the temperature we can survive at goes up. And I felt it important as a scientist to put this in because, at least in the US, there's so much media coverage about this. And people are not understanding the complexity of these analyses and what needs to be done. Equity is at the heart of everything with climate change and health. And that's true also for heat. There was a process in the United States in the 1930s where city planners, often mayors, took a map of the city and actually drew a red line around certain neighborhoods. And those were neighborhoods where the poor and the marginalized were allowed to live. It was very difficult in those neighborhoods to get mortgages. This has had consequences since the 1930s. And this process in the US is called redlining. And this is for one particular city in the US. And this shows the red line districts from the 1930s. And those districts are still hotter today. That when you go and measure the temperatures, they're still much hotter today. Fewer trees were planted, different kinds of construction material was used, houses were more closely spaced. And so when we think about equities, it's not just only the current equities, it's the historic inequities. And how choices that were made have continued to affect populations today. I could go through these cities, but you can see the temperature changes up there. And what can we do? There's lots we can do to help with planning. This is a tool that was recently put out by my group for the state to take a look at the different kinds of factors that can affect vulnerability to heat. It's not just the temperature, it's the age. What's the demographics for a particular place? Was redlining a practice in the 1930s? It was in some places in the state of Washington, not in others. What proportion of the population might have diabetes, heart disease? And all of that can be brought together to help city planners think about where they need to focus. This kind of vulnerability mapping is becoming much more common. And I think you're going to see it in many more places for other issues as well. Going into a changing future, I put this in, again, I'm focusing on the United States just because I've got lots of graphics for them. And I don't want to talk about Australia. You know all of your science here. I put this in because it's one of the few studies that looked at both adaptation and mitigation. It looked at heat-related mortality towards the end of the century, considering adaptation and mitigation. So if you look across the bottom row, there's adaptation, top row, no adaptation, high emissions on the left, low emissions on the right. And all you have to do is compare the upper left to the bottom right. Those are very different futures. And that speaks to the urgency of both adapting and mitigating. If we do one alone, we're not going to get to the kind of future we would like to have. The other point is you look at the bottom right, even with adaptation and mitigation, because of population aging, we're going to see an increase in heat-related mortality. They'll have consequences for our health systems. Most of the projections around heat-related mortality say what could happen in the future. Right? We'll take a population, we'll look at the exposure-response relationship, we'll make assumptions about temperature change, and we'll do pretty much what the previous study did, which will project how many people could die from heat. This is a study from Stockholm that did something quite different. It said, let's assume that current heat-related mortality is acceptable. It's not. Almost every death in a heat wave is preventable. There's no reason anybody should die in a heat wave. But we'll just say it's acceptable. And looking at older adults towards the end of the century in Stockholm, said how much would we have to reduce the vulnerability of older adults to keep heat-related mortality the same? This is the first time anyone did this. The answer is relatively shocking, that the vulnerability would have to be reduced by 75% to keep heat-related mortality the same. And frankly, collectively, we have no idea how to reduce vulnerability that much. And this is an area where it's really important to start thinking about how we can better protect vulnerable populations and go beyond what we've been doing so far and become much more comprehensive in our approach. A critically important approach is heat wave early warning and response systems. And I'll emphasize and response. I often make fun of our local meteorologists because until we got a heat wave early warning system a few weeks ago, they would say, you know, today's hot. Mostly people figure out that today is hot. Not everybody does, but most people figure out today is hot. But what do you do? And a couple of years ago, the World Meteorological Organization set up this risk and early warning initiative. And you can see the numbers of how many people have already been protected. By the end of this initiative, they want to protect half of the population in the world from not just heat, but flooding, wildfires, and other hazards. And significant investment is going into this. Billions are being spent to develop more early warning and response systems. One element of that is a collaboration between the World Meteorological Organization, the World Health Organization, called the Global Heat Health Information Network. And this is their landing page. It shows where case studies are located. It's an effort to try and learn lessons across the hundreds of heat wave early warning systems around the world. What works, what doesn't work. How can these different warning systems be used in other contexts? What is it that we can share from these? And so this is quite an active network to try and make sure that we understand as well as we can what can be transmitted to other sectors. An example of a heat wave early warning system comes from the UK. Their system's been in place since 2005. It's one of the longest heat wave early warning systems in the world. It has a monitoring and evaluation program. So they meet at the end of the heat wave season. They talk about what worked, what didn't work, what do they need to change. They meet again right before the heat wave season starts to figure out, do we need to update any phone numbers? It never fails that when you have some kind of emergency, somebody has their cell phone turned off and you can't find the backup. So they make sure they have all of that in place. You can see that they chose to have 4 warning levels. And it's interesting, around the world, there's different choices in the number of warning levels. In the United States, we always have 3 because we've got a tornado early warning system that's been around for 100 years and everybody's used to that. And so we have 3 levels of warning, but you can see that there are 4 in addition to long-term planning. I will not go through this. It's just to put out one page from their document that they've worked out the roles and responsibilities at all levels. So what is it that local health planners need to do? And so everybody knows what they need to do when these events occur. Most of these systems are not quite as complicated as this, but this shows you all the different people, different organizations, different institutions, elderly care institutions, who works with the unhoused, and finding all the trusted voices and different groups to engage in these systems so that they can be as effective as possible. The massive heat wave they had a year and a bit ago, despite the system that's been in place for almost 20 years, there was more than 2,000 excess deaths. That the system wasn't prepared for a really extreme event. And that's something that they are working on to make sure that the next time they have one, they will be better prepared. There's lots of ways to help people be better prepared, lots of ways to help people keep cool without having access to air conditioning. We don't have to air condition everywhere. There's places we will. Elderly care institutions will need some air conditioning because people can be very frail and suffer quite a bit in the heat. But for many people, air conditioning is just not necessary. These are more infographics put together for a series in The Lancet about heat and health of different ways people can keep cool without using air conditioning. These infographics have been translated into Hindi because of all the heat waves in India, into Spanish. They're used quite extensively in parts of the US and Spanish-speaking regions to help people understand what to do. So there are materials here that can be used to advance early warning systems. One of the ones that is more in the longer term planning is making sure there's sufficient tree coverage. There is a goal in the EU to have all cities have 30% coverage with trees. And so there's analysis from IS Global that came out and said, what if we achieve that? How many deaths could we prevent in a heat wave? And the numbers are large because you can help reduce the temperatures and give places for people to go to be cool. So data are coming out on different kinds of interventions that are effective at shorter and longer term scales. I've been focusing on heat. That was my mandate, but wanted to point out that it's not just heat. I live in the Pacific Northwest. You think about heat, you think about wildfires. And that's true in so many places in the world. This is a situation that in climate science is referred to as compounding and cascading risks. I like the figure on the left. It's a unique way to show the kinds of interactions that can lead to different adverse outcomes. On the right are some examples for infectious diseases. Just pointing out that when we talk about morbidity and mortality, again, we're only looking at a slight slice of all the possible consequences for our health and our well-being. And we need to find better ways to understand the breadth of these challenges so that, in fact, we can be much more effective in being prepared. The wildfire figures just show you the trends in wildfire smoke across the last, I think it's about the last 20 years. It's about the last 20 years. And just showing the big increase in wildfire smoke. A point on wildfire smoke is that air pollution is measured by particle size, not by particle content. And that's because there's a particular particle size, it's particulate matter 2.5. And that is of interest because for that particle size, when you inhale it, it goes down into your lungs, deep into the lungs. It can be absorbed into the lung tissue and then cross the lung barrier and go into your body. And there's, I don't know how many thousands of studies of PM 2.5 and all the adverse consequences for mental health, for fetuses, for people with chronic obstructive pulmonary disease, for children, for others. But all of those studies relate to smoke that comes out of tailpipes. There are studies coming out from toxicologists looking at wildfire smoke, and it's at least 3 times as toxic as what comes out of tailpipes. And further, there's lots of work that needs to be done in this space as well, that most of the studies, when you look at what comes out of tailpipes, it's relatively constant pollution. You know, it varies over the days, but it's relatively constant. The exposure to wildfire smoke is not. The neighborhood I live in a couple of years ago, we had really extreme measurements of particulate matter, but we don't know what that means for growing lungs to have short but very high exposures. For those of you who are looking for research subjects, there's many here that can be followed. When we're thinking about climate change, we, of course, are looking into the changes in the future. Every assessment cycle from the Intergovernmental Panel on Climate Change is an iconic figure of what could happen with global mean surface temperature under different assumptions of emissions. And traditionally, those have just been curves that are published in newspapers. But Ed Hawkins, who was really recently on campus, will be on campus, came up with the warming stripes, which are a great communication tool to help people understand how much change there's been and what the change could look like under different assumptions of greenhouse gas emissions. And there's 5 set of assumptions. And this one, yeah, they did 5. This was the first time people were put onto this figure and showing that there's real strong cohort effects, that somebody's life course is going to be very different if they were born in the 1980s from children born in the 2020s, because our exposures are going to be very much different. And it gives us opportunities for thinking a little bit differently about how we do our research to get better understandings of these cumulative impacts under different exposures that will start at birth. And with that, I will end with heat is an all of society issue. We need to think of it from that perspective. And hopefully I've convinced you it's urgent that we address both adaptation and mitigation so that we can protect, frankly, ourselves right now, but also future generations. Thank you.